Here's some, oh, good, got it. Okay. Here's some logistics. So if you're an in-person attendee, we recommend that you also join the Zoom. And be sure to mute your computer so that we don't get any feedback. And in the Zoom, we would ask you to change your name to be your first name and your last name. And in order to do that, you click participants and then more next to your name to rename yourself. You can click the CC button to toggle captions and view the full transcript if you like those sorts of things. The session is being recorded. Everyone got muted on default when joining Zoom, but you can unmute and ask questions, or you can ask in the Google Doc. And so this is the Google Doc. I think that's going to be shared in the chat as well. And so if you have a question, just put your question in there and we will answer it. And then we would really love it if you would do our survey afterwards to let us know how you like the course and what we can do better for next time. Okay. And one little piece of logistics that I would like to add here is that I have what I hope is temporary hearing loss, but it seems to be getting more permanent by the day. So I would appreciate it if people would speak very clearly and very loudly when they ask me a question, and I will repeat it. And especially people in the room, I actually have trouble hearing people in the back of the room. So you can speak really loudly so that I can hear you. I'll repeat the question. I'll make sure I got it right. I'll also try to read your lips to figure out what your question is. Okay. So let's go ahead and get started. See if I can do this. Oh, sorry, we've got additional logistics. My bad. So the slides and videos will be available on our training event page. And then also, we're going to have Perlmutter office hours weekly, but different days of the week. We're trying to do different days of the week in case people can't make it on a particular day. And so we would invite you to attend some of our office hours. They're 1.5 hours on various weekdays. You can look it up on our website. You can see the URL there for our office hours. And what that is we just we have kind of one-on-one with you on any kind of issues that you might be experiencing, or any ways that we can help you with something having to do with Perlmutter. Okay. So, okay, one more thing. So if you're going to do hands-on exercises, which we hope you will, you want to log in. So you use SSH to log into Perlmutter. And then you're going to land on a login node. You want to CD to your Scratch directory. And then you want to do git clone of this. And I think this is also in the Q&A doc, right? All these instructions. And so that will give you the exercises that we're going to do. And it will also give you the answers. Okay, and then there's some good references for how to run jobs and how to run interactive jobs. And those are available on the nurse documentation website. Okay, we have made a reservation for this course today. So it is going to start at 10:30, which is when hopefully we will start doing the hands-on. There is a project called TRN012. You have been added to it, or you have an account that's in there. And that training project is valid through June 30th, so you can continue to use it for one more week. But for today, from 10:30 to 4:30, we have a reservation, and you add just this in pink here, this reservation equals crash course, etc. For any kind of jobs that you're going to be submitting, and then that will get your job into this reservation, and it should start up immediately. If it's not from 10:30 a.m. to 4:30 p.m. today, outside of those hours, then you don't need to use the reservation flag. You might still need to use the -A if you want to charge to TRN012. Okay. Okay, one last thing I want to remind you of the nurse code of conduct. So when you signed up for a nurse account, you agreed to our code of conduct. And so just want to remind everyone that we're going to work together professionally and productively towards our shared goals while respecting each other's differences and ideas. And we should all feel free to speak up to maintain this environment. And remember, there are resources available to report any violations of the code of conduct. And so you can email us at nurse-training@lbl.gov for any concerns. You can also look at our code of conduct. There are 4 different ways listed for you to report any violations of code of conduct. Okay. With that, I think we're going to actually get started on parallel programming concepts. That's still me. Okay, can't remember. Y'all just got back from vacation. This is my first day back. I have no idea what's happening. Okay, so first we're going to talk about parallelism. Okay, so I like to just kind of talk about concepts of parallelization, differences between serial and parallelization strategies, and just give you an overview of this in a way that actually doesn't really involve any coding or anything. Okay. So parallelism really is it's a way that we can work smarter by simultaneously tackling multiple tasks. So the concept here is that we're going to divide a task or problem into smaller subtasks that we can execute simultaneously or in parallel. And the great thing about this is if you can do that, you can get your work done faster because you're doing it in parallel more efficiently. Okay, so it applies to, you can parallelize just about anything, including things that have nothing to do with programming. So one example is making dinner. So let's say we're going to prepare a lasagna dinner. Okay, I hope most people at least kind of understand how to make a lasagna. You know, maybe you don't know the recipe, but you kind of understand the concept of what a lasagna is, but how it might be prepared. So if you think about making a lasagna, there's some tasks that you have to do in a particular order, right? So you have to like make the sauce and all the tomato stuff, right? You have to assemble the lasagna and then you have to bake it. Like you can't bake it first and then make the sauce, right? Like that wouldn't make any sense. So these things have to be done in a particular order. But then there are other things that do have a particular that don't have a particular order that you can do independently of one another. So a lot of times, like when you're going to make lasagna, you have to make some sauce. You also have to prepare the noodles. Like you have to cook them, boil them, right? So you could do those in any order. Okay, it's just some things that have to be done in a particular order. Okay, so that's the difference between serial and parallel, basically. Serial tasks have to be performed in a particular order, right? Like sauce, assemble, bake, serial. Parallel tasks, like making the sauce, preparing the cheese, those can be performed in any order. It doesn't matter if I make the sauce first or if I grate my cheese first, right? Doesn't really matter. Okay, so so that is kind of the difference between things that are serial versus things that are parallel. Okay. Okay, so we're talking about lasagna again. So our serial tasks are like I explained already, making the sauce, assembling the lasagna, baking the lasagna, right? We're gonna make a salad as well. We've got to wash up our lettuce and our veggies and stuff. Then we've got to cut them up and then we assemble our salad, right? We can't do it in any other order. Okay, but parallel tasks, like on the larger scale of things, right? I can make the lasagna at the same time as I'm making the salad or I'm setting the table, right? Like those, it doesn't matter what order I do those in. I just have to complete them before I can serve my dinner. Okay. All right. Does anybody here like to cook? Like especially like make a big meal, like, for example, make a, Thanksgiving dinner, something like that. Anybody? Yeah, all right. I happen to really enjoy doing that. So, I like to kind of figure out all the dependencies of my dinner. So like if you have your Thanksgiving dinner, right, you've got to make your turkey, right? It takes a couple hours for the turkey to cook, right? So you have to think about, okay, if I want to serve dinner at 5 o'clock or whatever, then I need to be sure to put my turkey in by 1 o'clock or whatever, right? So you can make sort of plans about how to do it. And so in this case, because I'm a total nerd, I made a plan here about how to make my lasagna dinner. Okay, so I'm gonna have lasagna, I'm gonna have a salad, I'm gonna have garlic bread. Okay, so you can see like these things here, like I gotta make my sauce, I gotta cook my noodles, I gotta grate my cheese. All those things, I can do those in any order, right? It doesn't matter when I do any of them, as long as they're all completed before I try to assemble my lasagna, right? Similarly with my vegetables, I gotta wash my vegetables, I gotta cut them up, and I've gotta assemble my salad. And for my garlic bread, I've gotta prep my butter, I've gotta cut up my bread, and then I can spread the butter on the bread, but I can't do that before, right? Like I can't spread the butter before I prepare it, or I can't bake it and then spread the butter, right? Like none of those would make any sense. So, but there are these particular points right here. You see where I've got like these three dependencies that are pointing to a symbol, and what we call those are synchronization points, right? So in my parallel algorithm of making dinner, right, I can do a lot of things in parallel, but some things I have a synchronization point where all of these prerequisites sort of have to be completed before I can go on to the next step. And so you'll find this is true also in other types of actual algorithms that you're performing. Okay, and then also like you can create kind of an optimal sort of a graph of how this meal is going to be completed, like the timing for everything. So everything in this previous thing, it was color coded, right? So anything kind of yellow is garlic bread, anything green is salad, anything red is lasagna. And so this is how I'm gonna do it. So like a lot of time, you're creating your sauce and then it's simmering. And while it's simmering, you can cook your noodles or you can grate your cheese. I don't remember which one of these is which. And then you assemble the lasagna and then it bakes in the background, right? While you're preparing your salad, and then you prepare your garlic bread because you want it to be hot when it comes out, right? And while it's baking, you can set the table and then you're done. Okay? Any questions about this so far? Any questions I can answer? Now everybody understands how to make lasagna. Okay, good. Okay, oh, I just moved on accidentally. Okay, well, so in this example, I see, like you saw in this graph here, basically, I parallelized it as much as I could for a single person to do this. But we could actually have several different chefs, each of them performing one parallel task. Personally, I have a sous chef in my house. He's 18. And so, if I'm cooking, I can tell him, okay, I need you to grate the cheese while I'm working on this other thing or whatever, right? So that's the concept behind parallel computing, is that you have like a bunch of chefs and they're all working together to create your meal. Okay, so next we're going to talk about jigsaw puzzles, because that has everything to do with everything, right? Okay, so let's say we want to do like a really big jigsaw puzzle, like a 10,000 piece jigsaw puzzle, one of those like huge ones. And let's say for the sake of argument that everyone can complete a puzzle in a constant amount of time, the same amount of time. It takes T hours for anyone to complete a 10,000 piece puzzle. So the question is, how can we decrease the wall time to completion? And when I say wall time, I literally mean the time on that clock that's on that wall, okay? So how can we decrease it from T hours to something else? So I'm gonna make some proposals about how we could do that. Okay, so let's say that we have our puzzle on the table and we have another person helping us. Okay, so we've got two people working on our puzzle. So tell me, how long would it take for two people to complete our puzzle? Any thoughts? So it takes T time for one person. How much time would it take two people? Go ahead.
Half of the time.
Half of the time, T over two. Yes, okay, that's a good thought. T over two, okay. Do you think it might take a little bit longer than T over two? I mean, ideally, in a perfect situation, it would take T over two, but in real life, it might take a little longer. Anybody have any thoughts about why?
It depends on the people ability of doing the puzzle.
Congestion, something like that.
Yeah, okay, I'm gonna assume, I know somebody said about the ability of people. I'm gonna assume that everyone can complete a puzzle in the same amount of time, which is not true. I recognize that. But yes, so there's some overhead involved in you and me working together, right? So for example, maybe I'm sitting there, really thinking hard about the puzzle with my elbow on the table, and right under my elbow is your piece that you need, right? That's one possibility. And so then you're gonna have to say to me, hey, Rebecca, could you please move your elbow? Okay, and so that's some time that is required that you wouldn't have had to spend if you had been doing the puzzle yourself, right? Another thing is maybe I'm working on a part of the puzzle and you're also working on a part that's right near it. So there's some resource contention where I have a piece that you need and maybe you have a piece that I need, sort of thing. So there's going to be a little bit of overhead, but basically, yes, it's going to take T over 2 hours or whatever to complete the puzzle. Okay, so let's make this more abstract. So let's say that the number of people is P people. Okay, so we can imagine with one person, it takes T hours, 2 people, T over 2 plus a bit, 4 people, T over 4 plus a bit. What about 5,000 people? Does that sound like a great plan or what? I mean, 10,000 pieces, each person just has to do 2 pieces. Okay, I see a lot of heads shaking. Like, Rebecca, no, why would you think of that? So what's the problem with 5,000 people around our table doing this puzzle? What's wrong with that? Any thoughts?
Too many people.
Too many people? Why? What do you mean?
The table is only so big.
Okay, that's a good point. My table, can I actually squeeze 5,000 people around it? Yeah, probably not. If I had a table that was big enough for 5,000 people, then, my puzzle would be like this in the middle, right? It'd be really tiny in the middle compared to the size of the size of the table. So yeah, might not be such a great plan. At that point, if you figure putting in a puzzle piece takes 1 second, let's just say that for the sake of argument. But each person finding 2 pieces that they could place would take way longer than 2 seconds, right? So then there's going to be a huge overhead at that point. So, okay. All right, well, I have other ideas about how to make a puzzle. Okay, so this is my, now I get to joke about this being the COVID-safe social distancing algorithm. So we have P people, and I put each of them at a separate table with N over P pieces each. Okay, and we're going to say, for the sake of argument, that all of the pieces that they get are all adjacent to one another. So it's not just like random pieces from throughout the puzzle. I don't know if you've ever seen, actually, my sister showed me, there's these advent calendar puzzles where you open a little box each day for 24 days. And anyway, so it's like that. It's like that. Okay. So what is the impact on our wall time? So if let's say we've got two people and, you know, I have half the pieces, you have half the pieces, right? And we're at separate tables. So what's gonna happen here? What's our wall time gonna look like in this sort of an instance? Any ideas? So there's some overhead that goes away with this plan, right? Like my elbow is not ever gonna be on your piece, right? So that's one bonus, but are there other kind of shortcomings that you might see to this algorithm? It seems like a genius plan, I can tell. Anybody?
You'll have to do a reduction to bring the halves of the puzzles together.
That's right, okay, yeah, so any kind of, yeah, my final answer, which is, you know, the puzzle all together, right? Everybody's gonna have to kind of bring each of their sections together and put them all together on the same table. And if you think about that, that's a pretty heavy lift, haha, no pun intended. You know, you're gonna have to have like your giant spatula that you're gonna put it under there, and you're just gonna have to walk a pretty long ways compared to just, you know, you and me across the table from each other, right? You're gonna have to walk a pretty long ways to go take your section of the puzzle and put it in with the completed puzzle. So there's a high cost for communication, let's call that communication. But there's gonna be less resource contention, at least until we get to that step where we're doing the reduction and putting everything all together. Okay? Okay. Does that make sense? Is there any other questions? Oh, I'm sorry. See, communication overhead costs. Yes, which tables get which pieces? So Anupam. In this case, we're just assuming that each table gets kind of a local section of the puzzle. And then at the end, then we're gonna have to figure out how to bring them all back together. Hopefully that answers your question. Okay. Okay, I've got one final idea. So we're gonna divide up our puzzle by the features on it. So, you know, usually these puzzles are like this big landscape that's really beautiful and amazing. So we're gonna divide up our puzzle by the features in the landscape. So there's a mountain, there's the sky, there's a stream, there's a tree, you know, you name it, it's on our puzzle here. So I'm gonna take the mountain, you're gonna take the sky, you're gonna take the stream, you know. How is that gonna work out for completing our puzzle? Any thoughts? Is this a good plan?
That'd be cool.
Yeah, it's great, okay. Problem solved, brilliant idea. Okay, somebody may have a comment here. Oh, thank you, Alexander. You might spend more time identifying which pieces belong to which feature than if you just separated it by local sections. Yeah, okay, you might spend some time, that would be an overhead that you would have to do. Identifying which pieces belong to which feature. But, you know, it might be pretty easy to figure that out. And then after we sort them, what other problems do you see? Are there any problems you could potentially see in this algorithm? Does anybody have any knowledge or experience with art, creating art? No? Okay. Do you know like what kind of the ideal sort of proportions are in a picture that are most pleasing to the eye? Well, I'll give you a hint. It is not having, you know, let's see, we've got 1, 2, 3, 4, 5. It is not having 20% mountain, 20% sky, 20% stream, 20% tree, 20% meadow, right? That is not visually pleasing. So we're probably gonna have, yeah, golden ratio, good, thirds, yeah, okay. And yes, Nathan nailed it. Depending on the size of the features, some tables may finish before others. That is exactly right. So if I, typically in a piece of art, you don't have like completely even geometrically, proportional stuff. You have one thing that might be bigger, you have another thing that might be smaller, so the mountain could be pretty big. The stream could be kind of small, so we're not gonna have like an even division of labor here. So there's gonna be some overhead from that because maybe I'm doing the stream, you're doing the mountain. I'm gonna be finished with the stream before you're finished with the mountain. Okay. Another challenge is gonna be that there's gonna be some pieces that, like for the mountain, for example, it's a jigsaw puzzle, right? So some pieces may be part mountain and part sky. Right? So then we could figure out a way to decide whether it's a mountain piece or a sky piece. Maybe if it's more than 50% mountain, then it's mountain. If it's more than 50% sky, it's sky. But still, there's going to be something at that interface between the mountain and the sky that's going to be kind of challenging. Okay, well, this ends our discussion of jigsaw puzzles, and we're going to move on to parallel algorithm design. Okay, so if you want to design a parallel algorithm, you follow these 4 handy steps in this acronym PCAM. Okay, so the first one is called partition. And so what we're going to do is we're going to take our algorithm that we have, our serial algorithm, and we're going to decompose it into fine-grained tasks in order to maximize the potential for parallelism. Okay, at this point, we're not thinking practically, we're just thinking of how we could divide this up. Whether it's a good idea or not remains to be seen. Okay, and our next step is about communication. And so we're going to determine the communication pattern amongst our tasks. Okay, and so what that means is basically it has to do with dependencies and which tasks are relying on other tasks for input. Okay, our third step is called agglomeration, and this is where we start to think practically about it. So we take our really fine-grained tasks and we combine them into coarser-grained tasks, if necessary, in order to reduce communication requirements or other costs. Okay. And then our final step is mapping, where we actually take our agglomerated tasks and we assign them to processes, subject to trade-off between communication costs and concurrency. Okay, so this should be, this is basically how you design any parallel algorithm. This is what I always go through when I think about a parallel algorithm. Okay, so next we're going to switch gears and we're going to talk about supercomputing architecture.
Can I ask a question about
Please.
like what you mean by fine versus coarse-grained tasks?
What do I mean by fine versus coarse-grained? Yes, great question. So when I say fine-grained tasks, what I'm talking about is, when I break it down into the smallest possible tasks. Okay, and a coarse-grained task, what I mean is I've taken those small ones and maybe I've combined a few into the same task. Yeah, great question. Thank you.